Okay, it gives me a great pleasure to talk on this subject, optimization, and that to constant optimization. I have been studying this subject for more than 20 years as a researcher and gone into quite a depth into various aspects of it. So, I would now put forward to you my own private version of this subject, and I have already given you an example of a constant minimization problem or maximization problem, whatever you want to call, when we spoke about the use of n dimensions, more than 3 dimensions, 4 dimensions. We gave an example of the diet problem and we formed what is called the linear programming problem, and that we had done. That was an important example of a constraint optimization problem. Here we are going to simply study, first to start with, a simple situation where we have to minimize a function of x y such that some x y is not free, that is not unconstrained like what we did in the last 2 lectures, but has to satisfy a condition like this, that g x y has to be always, so x y must be within in the level curve of this function g. For example, if you want to say maximize, you want to maximize a function of x y over x square plus y square equal to 1. So, this is an example given in the book, but I will talk about Lagrangian multiplier rule in my own way, and you must be ask me why there was one constraint. In the linear programming problem that you have said, there were a couple of constraints, more than one. But yes, here we are just talking about the situation, very preliminary situation, which first arose in the natural sciences, and Lagrange actually used his technique not while studying optimization as per se, but while studying mechanics. Mechanics is the key to many subjects that have come as a part of mathematics, or rather applied mathematics. So, suppose we want to do this, and suppose the function has a graph. So, here is your so this is your x square plus y square equal to 1. So, basically I am looking at this is my constraint set. So, I want to bother about the maximum value of fxy for all xy among all the xy's which lie here. I am not bothered what happens here or outside this circular circumference. So, if the graph is for example like this, so what you do, for example, graph is like this and the inner graph is like this. What you do essentially, you draw the cylinders, basically you draw from every xy you touch the function value z, you keep on drawing cylinders. You basically construct a kind of cylinder. So, basically at every xy on this circle you are evaluating the values of z, right. Also you have things inside and so forth. You will see among these at this particular point here, which drops down to this place, this x naught y naught maximizes the function value over this. Now, this maximum may not always be the maximum over Rn. The maximum over Rn could be here at this point. If you drop it, it is here, but maximum over this space is this particular zone is different. Further, you have to also come to the fact that we can also talk about local minimizers and local maximizers. So, I will define now local minimum. You have to yourself sit down and define what is a local maximum. But here you have to understand that we have constraints. So, we will first define a constraint problem. So, what we do is we consider to minimize f of x y, where x and y are real variables, such that g x y equal to c. We consider the minimization of this. Now, we have to talk about a local minimizer. X naught y naught is a local minimizer if x naught y naught is feasible, that is feasible means g of x naught y naught satisfies the constraints. This is called a constraint. So, in optimization language, this is called the objective, f x y is called the objective, and g x y is equal to c is called a constraint. So, if anything, any point which satisfies the constraint are said to be feasible for that problem, because those are the points we are interested in and we are not interested in other points. So, optimization, by the way, is a generic name given for maximization and minimization. It could mean either, but mathematical optimizers usually speak in the language of minimization, economists speak in the language of maximization, engineers speak in the language of minimization. It depends on what context you are speaking, because economics you are talking about maximizing profit, maximizing utility, engineers are talking about minimizing some kind of some kind of load or some kind of current or some issues. So, x naught y naught is a local minimizer if it is feasible and there exists delta greater than 0 such that for all x y which is in the open ball around x naught y naught, and you know what is the open ball, the norm of x y minus norm of x naught y naught must be strictly less than delta. These are such points for all x y in this such that g x y is equal to c. We have, so you have to understand, we cannot just take the ball and take points from the ball. We have to take only those points in the ball which satisfy the feasibility condition, satisfy the constraint, and that is the important thing that we have to remember. We have f of x y is equal to f of x naught y naught. So, writing the definition of a local maximizer is not a problem, because you have to, the story is same, just change the inequality. So, I am not going to talk about a local maximizer. Global maximizer you understand, where you just say that for all x y, you do not say this, such that for all x y which satisfies this, I have this. So, but the story that we are going to talk about is for a local local minimizer. The main theorem is actually written for a local minimizer. Now, let us look at this problem. Minimize f x y such that g x y is equal to c. all simple purposes we set for simplicity in the exposition we set C is equal to 0, and in doing so we lose no generality, we do not have a loss of generality, which means that I can always, instead of gxy, gxy can be replaced by g tilde xy, g tilde xy is equal to gxy minus c. So, our constraint can now be written as gxy, g tilde xy is equal to 0. So, without loss of generality we can always take c equal to 0, and hence we shall now focus on the problem Now, if I want to solve this problem, what should be my first thinking? Let me just try to understand that. Let us try to understand that algebraically. For example, if I have, say, minimize x square plus y minus 1 whole square such that, so you minimize over x y such that x minus y is equal to 1. Or x plus y equal to 1. So gxy equal to c. So or x plus y minus 1 is equal to 0. Basically, if this is what I have written, then I can see that I can, from here I can always write, I can convert the unconstant problem into constant problem into an unconstant one by just setting y to be 1 minus x, and then solve the unconstant problem minimize over x, x square plus y minus 1 is equal to minus x square. So, I am replaced it here because I can write it like this, I can do this. So, what I have? So, this is 2x square. So, you know the answer is 0. You say x is equal to 0. If x is equal to 0 is the answer, y is equal to 1. If you minimize this, I have x equal to 0. If x is equal to 0, then from the constant I have y equal to 1. So, if you see, this is a non-negative function because this is x square y minus 1 whole square. So, if I put x equal to 0 and y equal to 1, it gives me the value 0, which is the least value of this function, because this is a non-negative function, all the values are greater than or equal to 0, because these are points lying on a circle actually of with center 0 and 1, center 0 1. So, you know, so I have changed the problem from this to minimizing over x 2x square, and you know what is the minima, and hence you can solve it. Now, you also know simultaneously. So, what is the idea? What if I write it in a very general framework? What is my idea? If in a general framework, I have the following idea. So, if I minimize fxy such that subject to or such that whatever you want to say gxy equal to 0. Suppose y is expressed as h of x, just like here y is expressed as 1 minus x, h of x is 1 minus x. Then I can write this problem as minimize over x f of x h of x, and then go on differentiating it. But that really need not happen every time, because this function gxy can be complex enough so that you will not be able to write it like this. Because for example, if you have x here some x square plus y square equal to 1, then you will have y equal to plus minus root over 1 minus x. So y can have two different values and then you are stuck, you cannot put it there straight away. So here, so what is the idea? The idea is that first you eliminate y and then you differentiate. Eliminate y, make this as a function of x and then differentiate. So the key idea behind in constant optimization, key idea is eliminate and then differentiate. So that is the key idea, eliminate and then differentiate. So that is what I am trying to tell you, that Lagrange said that swap these two words. Lagrange says first differentiate and then eliminate. So what does, so let me write it down here, I am sure you have taken down the diagram. So Lagrange says first differentiate, just reverses the whole policy, first differentiate and then eliminate. This is the key approach, key idea behind the Lagrange multiplier rule. First eliminate and then differentiate, sorry, first differentiate and then eliminate. What he does is he forms a function called the Lagrangian function. So he forms a function called the Lagrangian function where he writes a combined function of the objective and the constraint with a multiplier associated with a constraint function, where this lambda is usually called the Lagrange multiplier. So this function is often called the Lagrangian function. It is good to hear some names. Lagrange was a great mathematician, by the way, spent most of his life in French, but a Italian mathematician from Turin. And Lagrange, if I tell you the way he used to work, you might be surprised. People do not work like that. So he used to start to work in the evening and then go working till the next lunch, and then he would take rest and come back again in the evening. That kind of dedication Lagrange had to mathematics. And so what did Lagrange said? Lagrange says in this first eliminate to differentiate, first differentiate and then eliminate, that you differentiate with this function with respect to x and then y, take the partial derivatives. That is, you basically take the gradient and then you take the one with respect to lambda and equate them to 0 and solve that system of equation. So what you do, so first, so you basically Lagrange says, okay, take the gradient with respect to x y. So I am just taking the gradient, I am just writing x y because just to say that, okay, x y has some value, of course, you put in something, you solve that system. So this, and also says you take the gradient just with respect to lambda. So keep x and y fixed up. So Lagrange says that if you solve these two equations, you can find an x y which satisfies this system, but if, so this is what is called the optimality condition or necessary condition for solving if there is a point is a local minimizer of this problem, minimize fxy subject to gxy equal to c or gxy equal to 0 for example, then these two are the necessary optimality condition, which simply says that grad of f xy plus lambda grad gxy equal to 0, and if I do this differentiation I will simply have gxy equal to 0. So, this is the system that he wants to solve. You eliminate the lambda, compute the x and y, but if you get such an xy, it does not tell me that it is really a maxima or minima. Only looking at the structure of the problem you can determine whether this is a maxima or minima or whatever. But how do you reach such a condition? How do you know that such a lambda exists? Because every time you may not be able to write like this y equal to hx, and here the implicit function theorem that you have learned, which I want you to go and see again, that would play a very key role, and that I really want to explain in the board. So, how the implicit function theorem is used. So, again we start by writing the problem. Now, the issue that comes in here is important. For every function, if it is a very implicitly written function like x y plus, so for example, if I write x y plus y square x plus x cube equal to 0. If I write something like this, you cannot write y equal to fx, y as a function of x cannot be written. What you have to understand here comes in the role of implicit function theorem. Suppose I have I know, suppose x naught y naught is a local minimizer . Local minimizer of fxy under the given constraints. So, assume that the following condition holds. Assume that del g del y x naught y naught is not equal to 0. Now, because it is a local minimizer, now since x naught y naught is a local minimizer, it must satisfy this feasibility condition. One must have g x naught y naught equal to 0, and you also have this condition, and these two conditions are ripe for application of the implicit function theorem. So, if these two conditions are met, this is always met if x naught y naught, see these necessary conditions assume this fact that we assume that we have a local minimizer and we want to see what condition it satisfies. So, if you know what condition is satisfied, you know that if you want to find a maximizer or minimizer, or minimizer in this particular case, we really have to figure out points which satisfy these conditions. You find the lambda x y such that these things are satisfied. Once we can do that, then we can further check whether maximization and minimization holds. I will give you as again I will write it down in your extra things which I will come within few days. I think by next Monday you will have it on your portal, that if you have f is a convex function and g is a convex function, g is a linear function, kind of a nice kind of convex function, linear function, then we will have the fact that whenever you have any point which satisfies the Lagrange multiplier rule will give me a solution. But if not, then we have to figure out on our own looking at the condition. Otherwise there are second order conditions which we do not want to get into, because that is pretty slightly advanced. Now suppose this is there, so what, so there exists a neighborhood, and a neighborhood is an open set, a neighborhood I am writing in short of x naught y naught such that for all there exists a neighborhood of x naught y naught and a neighborhood of x naught y naught and a function h defined on that neighborhood. So that is a definition, function is defined from neighborhood to R, defined on that neighborhood, I am writing in short NBD, such that for all x in the neighborhood in the NBD, I am not writing the technical things, just telling you stories. So we would have gx hx equal to 0. So basically in that neighborhood y's are expressed as y is equal to hx. So function has an explicit representation in that given neighborhood. So which means now in that small neighborhood around x naught y naught, the function, we have an explicit representation, the function can be, from here we can write y can be represented as h of x naught, thus becomes a local minimum of, becomes a local minimizer of phi x is equal to f of x hx. So we have replaced y with hx. So in that local zone x naught is the minimizer, because x naught is the local minimizer, because hx naught is y naught, hx naught has to be y naught, right. And so if you take any other point xy, it is of the form y is of the form hx in that neighborhood. So you have a neighborhood at where this feasibility is satisfied, plus because x naught y naught is already a local minima, there is already a neighborhood around x naught y naught such that fxy is always bigger. So you consider that part, the neighborhood so small on which this is satisfied, you can get a neighborhood pretty big, but you can consider the neighborhood to be contained inside the neighborhood where the local minimizer stuff holds. So what happens, that x naught becomes a local minimizer of this. Listen to this talk, stop it repeatedly, do back and forth and listen to what I have said. So you have x naught y naught which is a local minimizer. So you have a neighborhood, a circular disk around it. So there are, and for all points on that, f of x naught y naught is greater than or equal to fxy if those points satisfies, for those points which satisfy gxy equal to 0. Now here we have a class of such points. We have a neighborhood around x naught y naught by the implicit function theorem such that this happens. Now so if that neighborhood is bigger than what the earlier neighborhood, but I can have a neighborhood smaller than this, basically if this neighborhood is bigger than the neighborhood used for the definition of the local minimizer, I can actually consider only a small part of it which is inside that local minimizing thing, okay. So which means that x naught becomes a local minimizer of this. So which means phi dash of x naught is equal to 0. But what is phi dash x? If you go by that, if you go by your chain rule, it is del f del x plus del f del y into del h del x, del y del x, which is y is h x, so it is h dash x. So basically it is x naught. These things evaluated at x naught y naught, I am not writing them. So evaluated at x naught y naught, that is x naught, here y naught is h of x naught, y naught of course is h of x naught, because it is x naught y naught is in that neighborhood. So this is 0, so phi dash x naught is this and this is 0. So instead of writing del f del x at x naught, we will just simply just write it. So again you know that 0 is equal to g of x h x. So again you take the derivative and use the chain rule, this will imply that 0 is equal to del g del x plus del g del y into, we are taking the derivative with respect to x now only, with respect to h dash x at x 0 basically 0. So here we have two equations. So from here I will conclude from here that del f del x is equal to minus del f del y h dash x naught. But what is h dash x naught? I can write from here, it is minus del g del x divided by del g del y, and del g del y is not equal to 0 at x naught y naught. So these are all evaluated at x naught y naught, x naught y naught. So if you want to be so clear, put x naught y naught. So this is non-zero. So what do I have from here? From here I have h dash x naught is equal to minus del g del x by del g del y, which is non-zero. This is evaluated at x naught y naught, evaluated at x naught y naught. I am not, I can also write on the sides x naught y naught. So if you want, you can, if you want the writing to be much more clearer, you can write like this, del g del x at x naught y naught, del g del y at x naught y naught, it is non-zero. So it is very, this is a absolutely proper math. This is minus of this, so that is what you get from here. So you put that back here, so you get del f del x is equal to del f del y del f del y divided by del g del y, all evaluated at x naught y naught. Del f del x also is evaluated at x naught y naught. If you, I am not writing x naught y naught every time, so I will not write x naught y naught, I will write x naught y naught at the end, so that I do not make the whole thing look very complex, and this is into del g del x. Okay. Now interestingly enough, if you observe what is del f del y, these are all evaluated at x naught y naught, please. It is nothing but del f del by del g del y into del g del x, del g del y. So this cancels and I have del f del y. So maybe, so what's important here is the following. So, I will now from what I have there on this part, from this part I will now take things from this part and come to take an hashtag and come to this part. Now I will set lambda is equal to del f or del f del x by del g del y evaluated at x naught y naught. This is my Lagrange multiplier, I am showing the existence of something. So, lambda I can put here as minus of this, then what I have? I have grad of f of, so this is minus lambda, this is minus lambda, this is minus lambda. So, I have at the end grad of f naught x naught plus lambda grad of g x naught y naught is equal to 0. And of course, you have g x naught y naught equal to 0. So, that condition that we have written earlier actually is satisfied, that is this is already known to you. So, this is the Lagrangian multiplier rule, it shows the existence, and the existence of the Lagrange multiplier rule, the Lagrange multiplier comes from the implicit function theorem, and that is the key idea that one has to keep in mind. And so, let us do an example here, and through that example we solve this problem. Okay. So, let us take one example and then try to see what we can get from the Lagrange multiplier rule. You can go to higher dimensions also, but I am not getting into higher dimensions with you at this moment. So, take a simpler problem, minimize f of x y equal to, I am taking this example from book, the standard one which you are using, subject to x square plus y square minus 1 equal to 0. If what is my f? So, instead of, if I call this just lambda, then I can write this as for example, instead of lambda I put lambda as minus mu, or I can replace lambda with minus lambda dot, lambda dash or lambda naught, then I can write this as grad f x naught is equal to lambda naught grad g x naught y naught. So, whichever way you can write. So, I am writing in that simpler form where grad f x naught is lambda times grad g x naught. It says that the two vectors are parallel, but they are linearly dependent. Grad f is linearly dependent on grad g. Those who know linear algebra, I am using for that terminology, and those who do not know linear algebra, just do not worry, nothing is going to happen. You just apply it mechanically. At least you know why such a lambda exists. The implicit function theorem that you have learned is actually working. So, math works, that is a very important thing, that is a very important reminder of this lecture. So, what you do is you try to find out an xy which satisfies this. So, here my xy is f is x square minus y square, it is 2x and minus 2y times g is 2x 2y. So, what do we have? We have 2x equal to lambda 2x minus 2y is equal to lambda 2y, and of course, we have x square plus y square is equal to 1. So, if lambda equal to 1, so from this equation what does it imply? Either lambda equal to 1 or x equal to 0. X equal to, if x equal to 0, whatever lambda you want, it will work. If lambda, if you put x lambda equal to 1, then whatever x you choose works. So, either lambda equal to 1 or x equal to 0. If x is equal to 0, then it implies that from this equation y is plus minus 1, because y square is equal to 1. So, if y is plus minus 1, say if I put y equal to 1 here, so I will get lambda equal to minus 1. If I put y equal to minus 1 here, still I will get lambda equal to minus 1. So, then it implies, so you will write the equation is A, B and C. So, it implies from B, here it implies from C, it implies from B that lambda equal to minus 1. So, this is what I now if, so from the first we also have another conclusion, if lambda is equal to one, it implies that if lambda equal to 1, if I put lambda is 1, okay. So, lambda means 1 means I can take any x. Lambda means lambda equal to 1 simply means I have to put y to be zeros here. If because I cannot put y to be 1 because it will become minus 2 equal to 2. So, if lambda is 1, then it implies from B that y is equal to 0, because there is no other choice. You would lambda equal to 1 for this equation, minus a is equal to 1 into is minus a is equal to a is any minus x equal to x holds only if x is equal to 0. Basically, if you would lambda equal to 1, you will have 4y equal to 0, so y equal to 0. So, y equal to 0. So, that implies from C x is equal to plus minus 1. Okay, that is what we have till now. So, now you have to see what are the eligible points, so what are the feasible points basically. The feasible points here are xy is 0 plus minus 1 with lambda equal to minus 1. So, these are the possible chances of maximizing or minimizing the problem. So, you can actually find maxima or minima, let us, so maybe I can make the problem more minimize or maximize, whatever you want, do both, let us try out both and see if we can get. So, there is another set of points xy where x is plus minus 1 and 0 with lambda equal to 1, because observe that when lambda equal to 1 we have y equal to 0 and x is this, when x equal to 0 we have y is this, and for that lambda is equal to this. So, these are the two situations. Now, interestingly enough, f 0 1 is equal to f 0 minus 1 is equal to minus 1. If you look at the function value, which is and f 1 0 is equal to f of minus 1 0, which is 1. So, you know which are the values which are maximizing, which are minimizing. Now, why these are maximizing and minimizing value? Why? That is the question we have not answered. How do you know that these are not maximizing and minimizing value? I can have something less than, I can have something worse. I can, this function value can be lesser than minus 1 or subject to this. But you have to observe, subject to this, it cannot have a value lesser than minus 1 or plus 1. So, how do we know that this problem has a maxima or minima? This goes back to the age old question of Weierstrass, which I have not mentioned here. So, if you take a set which is closed and bounded in the sense that it is a kind of boundary and its in the sense that all the x's, the norm of all these x's in this set is less than some given number. So, it is bounded, and closed means the set is something with a boundary. For that kind of sets, Weierstrass said that if you have you want to have maximize or minimize a continuous function over it, you will always find points inside the set which will have a maximizer and minimizer, and that what these books do not explain, that because of the Weierstrass theorem that a continuous function can be maximized or minimized over a closed and convex set. It is bounded over a closed and bounded set, and there are points in that set where the maximum value and the minimum value would be achieved. So, because such maximizers and minimizers exist, and that maximizers and minimizers must satisfy this Lagrangian multiplier rule. So, whatever points which have satisfied the Lagrangian multiplier rule, we have checked with them what are the values have been observed. So, the maximizer and minimizer must the maximizer and minimizer must lie among them, and so the 2 gives the minimum, the -1 is the minimum value and +1 is the maximum value. So, it is the Weierstrass theorem which we know for a function of one variable, that if I take a function of a real variable from a closed interval a b to r, then the function is bounded on the interval a b, and there are points points x1 and x2 in the interval a b such that fx1 is the maximum value and fx2 is the minimum value of the function. The same story can be repeated here, where a function of 2 variables is continuous, but the set that you have is closed and bounded. I am not getting into the geometry in too much detail, but that is what it is. Because of that Weierstrass theorem, you know that there are minimizers and maximizers are existing, and you get the points which satisfy the Lagrangian multiplier rule, and you have jotted down the functional values, and you know what is the maximum value and minimum value, and you know that the maximum value and minimum value would exist. So, and you know which are the maximizers and which are the minimizers, and with this I end the talk and hope that you have enjoyed it, and hope that you have enjoyed this proof which shows the power of the implicit function theorem. There are many ways to prove the Lagrangian multiplier rule. People are still publishing papers like a short proof of the Lagrangian multiplier rule, an elementary way to publish the Lagrangian multiplier rule. They are still coming in actually. So, the interest with Lagrangian multiplier rule has not waned out, it still is extremely important in science. Thank you very much, see you in the next class.